Hey everybody, welcome to the Interactive Immersive HQ. My name is Lake Heckerman. I'm a new media artist and creative technologist based in Brooklyn, New York. I work on a variety of interactive installations and permanent exhibits around the world, and it's my pleasure to be here working through a series of quick and easy GLSL techniques to help everybody kind of get accustomed with something that might not be super intuitive to begin with, and also create some pretty cool stuff in the process. Today we're going to be looking at creating a Voronoi effect using only GLSL, and we're going to do so hopefully without too much trouble. As you can see here, we have a nice component. It'll be able to take in any image. It will perform the Voronoi tessellation using a selection of points, which we can render or not render, and use a lot more points or a lot less depending on what we're interested in doing. So I'll scale this down, I'll add the points back a little bit so that we can see. And before I jump into it, I will take a second to just talk about what a Voronoi tessellation is in case somebody isn't familiar with it. A Voronoi tessellation is very, very common. I expect that everybody watching this tutorial has probably seen it at some point, but at a very simple level, what a Voronoi tessellation is simply scattering a set of points over an image or a texture plane and determining the color of each pixel or point on that plane by its location, or rather by what point is closest to it. So we have a bunch of pixels, we have a bunch of points. Every pixel looks at all of the points and determines which point it's closest to, and that is what determines the color of that pixel, resulting in this tiled cell looking pattern, which is very common and often found in nature. Here is a little simpler and static example where you can see they have these points, and all of this like light purple color is the pixels that are closest to this specific point. All of these pixels are closest to this dot, the blues here, so on and so forth. So we're going to recreate this in TouchDesigner using a GLSL shader. Here's the effect that we're building. You can see there's not very many tops, so it is pretty simple, all things considered, and we're going to be recreating all of this from scratch. So I will just delete that and we can get going. I'll drop down a base. I'm going to keep this movie file in. It's just the Trillium stock photo. I'll jump inside my base. I will first add an in. I'll call this in text. I'll go up a level and I'll wire in my movie file in. So the next thing I'll do is I'm going to drop a null, and I'll just call this null text, and then I'm going to drop a GLSL afterwards. It can be the GLSL or the multi. I generally just defer to, or default to the multi, because there's no difference but the number of inputs. You never really know how many you end up needing. And then I will drop an out after this, and the first thing that we can do is simply pass through our color to make sure that everything is working. That is super easy. I'm going to edit the shader. I'll put my TouchDesigner over to the left side of the tab, and my nope, that's not the right one. My cursor editor here on the right side. Oops. Okay. So very first thing I want to do is simply get rid of this second line, uncomment out that first line, and now we have a pass-through shader. I will also simply have a comment at the very top that says Voronoi effect. So now that we know what we're doing. So the first thing that we need for building this Voronoi effect is a list of points. Now, there's a bunch of ways that we could get a list of points in TouchDesigner, but I think the simplest way is going to be just using a noise top. So I'm going to use a noise top. I'm going to set it to 32-bit float, make sure that my offset's 0 and my monochrome is turned off. I'm going to set the resolution then to 1 pixel wide, and I'm going to customize my component, and here's where I'm going to have a number points parameter. That's going to be an integer, and that will go from, let's say, a default of, I like maybe 500 as a default. I'll make 1 my minimum, and I'll make 1,000 my maximum. And we can go ahead and clamp that min to a 1 so that we don't end up going to 0. I'll then right-click, open my parent parameters, and drag and drop this number of points onto the X resolution of my noise. Now I can turn on the viewer. I can press V, and we can see these points arranged in 3D space. So there's 500 points. It's looking all right, but we want these points to be 1, just on the range 0 to 1, so that they kind of fit on our texture plane, 0 to 1. And we also want those values to be clamped to the XY plane, meaning we want their Z value to be 0. Now, I'm going to press V again to turn off the viewer there, and I'm going to use another GLSL to do a quick edit. We'll uncomment this first line and delete the second line again. This is just, again, passing through those values. And here, I'm going to wrap point locations around the range 0, 1. And we can do that by simply, well, first, maybe I'll create a little, to make this readable, a vec2 called pose equals color.rg. I'll wrap the points around the range by using pose equals mod pose comma 1, and then we'll set color.rg equal to pose and output that color. We can further use color.b times equals 0 to clamp all positions to the XY plane. Now if I turn on this viewer and press V, we see that all of our points are now nicely between 0 and 1, and they're all on the XY plane, which is just what we wanted. Now, there's clear pattern here. We can decrease our simplex noise period down to like 0.1, and this is looking a lot more like a random point distribution. We will get to some extensions on that later. For right now, I'm just going to take that, add a null after this GLSL, call it null points, and this will be wired into my shader as the second input. Now I'm going to go back to the Voronoi effect shader, and now we can kind of start going through the actual shader code that will be required to get us an image that looks like something. All right, so in this case, the first thing I want to do is improve best practices a little bit when it comes to sampling textures. And a nice way to do that is by using the hashtag define syntax to set up some texture placeholders that we can use in our code. So for example, I can define the letters capital SRC to be 0. And what this means is that anywhere the shader sees these SRC value or letters, characters, just like this, the compiler will replace those characters with whatever we define afterwards. So in this case, 0. So if I replace this 0 with SRC, when the shader is compiled, it actually is still reading this SRC as a 0 because that's how we define this macro. These are called macros. We can define another one called points and set that to 1. And that way we can also, let's say we were to switch these input values, right? So now this is, our points is our 0 input and our texture is our 1 input. This makes it really easy because we can just change this 0 and 1 in such a way that will allow us to easily output our shader. And I guess to see that, we would just need to make this a custom resolution. And so now you can see that if I just switch this 0 and 1, what is displayed changes, which is really nice because sometimes you reorder your inputs and things get all messed up, and this is a nice, easy way to kind of control against that. I guess at this point, we might as well drag and drop our shader resolution, and when you drag and drop it onto this component editor, you'll have this option, set reference expression on source. And now if I go back to my parameters, I can make this 1920 by 1080, and so now we have that resolution in our shader. Okay, so now what do we need to do? We need to read in and get access to all of our points, right? We need to find some way to iterate over all of those points and determine which point is closest to our given pixel. And then we need to use that closest point to determine the color of our pixel itself. So the first thing that we're going to need is a way to loop through all of the points and just like understand that we are looping through all of those points. So I'm going to define a function. We're going to use a circle function to just draw a little circle where all of our points are. So we can do that. We can create a function. It'll return a float value. We can name it circle. And what does a circle need? A circle needs a vec2 UV, which is the current point. It needs a vec2, which is a center. And then it needs a float, which is going to be that circle's radius. Now, we're going to have another vec2. We're going to call this aspect UV, and this will be equal to our UV. Actually, maybe it's helpful now if we set up an aspect ratio uniform before we continue with the shader. A uniform is a value that's going to have a single number that's used for every single pixel the shader operates over. So to set that up in our shader code, at the very top, we will write uniform. In this case, it's going to be a float, and we'll call it UAspect. In our GLSL top, we can go to the Vectors tab and add a vector called UAspect as well. And we can use our resolution parameters to calculate the expression for this UAspect, which will be our resolution Y over our resolution X. Now we can use this aspect, UAspect uniform anywhere in our shader. For example, right here, we can say uv.y times equals UAspect, and this will aspect correct our UV values used to draw circles at points. So now we have to take the center and also aspect adjust that. So we'll have another vec2, we'll call it aspect center, and that will be equal to our center variable, parameter. Then what we need to do is do the same thing, center.y times equals u aspect. And this will aspect correct the circle center coordinate as well. Then the last thing that we need to do is actually draw our circle, and the best way to do that is to use smooth step. So float c equals smooth step. This smooth step is a function, a built-in GLSL function that returns, well, it takes in parameters. Those parameters are edge 1, edge 2, and value, and it will return 0 if the value is less than edge 1. It will return 1 if the value is greater than edge 2, and it will return a smoothly interpolated value between edge 1 or between 0 and 1 if the value is between edge 1 and edge 2. So in this case, our edge 1 is going to be our radius. Our edge 2 is going to be radius minus some very small value, like 0.001. And our value is going to be, in this case, the distance from our UV to our center. And we can use the distance function in GLSL, which is simply distance, and then we input our aspect UV as argument 1 and aspect center as the second argument. We can then simply return C. And so now we have this way to draw a circle. We can say color plus equals circle vuv.st comma vec2 0.5 0.5 and a radius of 0.1, and this should draw us a circle in our center, but it is returning a float and our color is a vec4, so we should really just add it to our red channel. And there seems to be a little error. Silly me. I just spelled circle wrong in my function declaration, which I'm sure you guys noticed before me. Okay, so now we have this circle that is being drawn. The aspect seems to be a little bit wrong, but I think that we can fix that if we just do something like aspect correcting this UV here. So we can say vec2 UV equals VUV VUV VUV.st UV.y times equals U aspect. And then we can use UV as our circle input. And then the vec2 can be 0.5 times U aspect as well. And now we have a nice aspect correct circle in the middle of our image. Now we don't really care about that, but this is just to illustrate that drawing the circle is indeed working. Now we need to loop through all of those input points, which remember we have 500 of them right now. We need to loop through all of those input points, and first I'm just going to draw them all. So the way to do that is to use a for loop in GLSL. But before we do that, we need to add one more uniform, which is going to be the number of points that we have. So I will use this unum points. I'll drag and drop this parameter number points from our parent onto it. And up here in our shader code, we will add uniform. In this case, it's going to be an int unum points. Now we have access to this value for all of our pixels, and we're going to do a for loop. So a for loop in GLSL is written as so, for, and then in parentheses, we start with a integer indices, so there's int I, and we're going to start with it equal to 0, semicolon. We're going to run this for loop until I is, or as long as I is less than our u num points, another semicolon. Then we're going to use I++, which means every loop through the loop, every time through the loop, we're going to add 1 to our indices. So we will loop through all points. And what do we want to do? For every point that we have, we need to first read it in. So we can do that by creating a vec2 and call it point. And here we're going to use a function called texelFetch. TexelFetch is very similar to texture, which you're familiar with. but instead of using a UV coordinate between 0 and 1, it's going to use an integer lookup value to grab the pixel values. So we will still use std2d inputs. In the brackets, we're going to write points in all caps because remember we set up this macro that's going to replace points with 1. So this is basically saying look at the second input, which is our points. The input that we want to use is going to be an IVEC2. And here we're going to use I as our X and 0 as our Y, because this I is going to be first 0, so the first point, then 1 for the second point, so on and so forth. And then the texel fetch function requires a last parameter, which is almost always a 0, and that's the level of detail that we're going to be sampling at. Finally, we can put .rg, which is swizzling to grab just the first 2 components of that texture sample for our X and Y components of our point. Now, we will have a float, we'll call it distance, or dist, and we'll use distance function again, and here we can use our UV and our point as the 2 points that we measure the distance from. Well, actually, we don't need to do that right now. First, I just want to color the points, I guess. And so for that, actually outside the for loop, I'm going to create a float that I'll call render points equal to 0. And every time through this loop, I'm going to use render points plus equals. And here I'm going to use my circle function, which will be called on UV, which is my current pixel. But I'll be using point, which is our current point, as the circle center. And then for the radius, I'll use something very small, like 0.001, maybe 0.02, like that. And let's see, I think I spelled that wrong again. I did. Circle. And now, hopefully I can just say color plus equals vec4 render points. And now we can see on our shader, especially if I get rid of this placeholder circle now, we have all of these points here that are drawn on our circle. And actually I just took away this aspect correct because we don't need that anymore since we're doing the aspect correction up here. We don't need to do it in our main loop again. And so now we are rendering those points. We should add ourselves a uniform float u point size. Add it here, u point size. And then we can replace this hard code with u point size divided by 1,000. And then if I make this like 10, it makes our points much bigger. And they're ovals, which is also not quite right. And the reason that that is not quite right is because we need to do one more aspect correct to be able to get these rendering as nicely aspect corrected circles. So we'll do that right now. So I actually think that I just made a small error, which is that we should be using aspect UV here and aspect center here. And by just making that change, we can see now we have some nice aspect corrected circles. I'm going to give myself a customized parent component. I'm going to add a parameter. We'll call it point size. I think that can probably be a float. And we'll default it to, I don't know, 2. We'll make the min 0, the max 10. Clamp the min at 0, and then drag and drop this bad boy onto our u point size parameter. And now here we are able to draw these points. Okay, That's most of the way there. So now that we have our points drawn, what we need to do is the Voronoi aspect. So now that we have all these points and we're already looping through them, we need to do the piece that measures the distance from each pixel to each point and determines what the closest point is for every pixel. So the way that we can do that is basically by first setting up a couple values outside of our for loop that will be our initial values. And for that, we'll need a float. We'll call it min dist, and that will equal to something very large, like whatever that is, 1,000,000? Yeah, like 1,000,000. And then we will set up a vec2, and we'll call it closest point, and we'll set that equal to vec2, something that's going to be way outside our screen, so maybe just like -10, -10. So set to off screen at first, and this would be set very large at first. Now, every time that we go through this for loop and we sample a new point, we're going to calc the distance from pixel to point. So that will be float dist equals, in this case we can use distance with our UV and our point parameters, or variables as function arguments. Now we can have a little if statement. You can say if distance is less than our min distance, then we want to set our closest point. Closest point is going to be equal to our point, and min dist is going to be equal to dist. So anytime we find a point that's closer than our current closest point, we update what the closest point actually is, and we also update what our new minimum distance is. So this is check distance against current closest point. Update if this point is closer than the ones sampled so far, right? And we're adding, we're rendering points, and we render the points no matter what. So that is outside this if statement. Now, the last thing that we got to do is actually just move this color sample all the way down to the bottom, and instead of using vuv.st, we can just use our closest point as the color lookup. And just like that, I make this full screen, we indeed have our Voronoi tessellation. And it's as simple as that. Now, the last thing that I might want to add is, let's say, a constant and a speed. We'll just use this to translate our noise. Of course, we won't have this be very high, just like a 0.01. Maybe even another parameter here on our parent called speed that we will set from, I think in this case, maybe like 0 to 0.1. Whoops, 0.1. Oh, it's set to an integer. It should be a float. 0.1. And then we can go customize our parent. Actually, instead, sorry about that, I want to open the parent parameters. We'll drag and drop the speed parameter right there. And now we'll go up a level and we'll take a look at our results. So I'll backdrop this, and here we go. So we have a animated Voronoi. We can turn the speed down or make it go like really fast. Turn it down. Can change the point size, make them bigger or smaller, or even not there at all. And we can add a lot of points if we want, which if you take the point count down and then make this like, maybe like 2,500, this tessellation starts to look pretty cool. And the more points that we have, the more the image is kind of resembled in the final tessellation. Careful though, because this is a for loop, so we are our complexity and our calculation speed is going to decrease as these points go up. So just careful on your graphics card, depending what computer you have. You might not be able to go up to 5,000. So just be cognizant of that. But otherwise, I think this is probably a pretty good place to stop this technique. Hopefully it was useful, and now you have a different way of thinking about how to use shaders to kind of complete these effects using arrays of input points. And I really like this Voronoi tessellation. So yeah, thanks for being here. See you next time on the HQ, and until then, happy creating.
Hey folks, thanks for watching. If you like our YouTube content, I highly recommend you check out the Interactive and Immersive HQ Pro. The HQ Pro is the only comprehensive educational resource and community for immersive design, TouchDesigner, and creative tech pros. In the HQ Pro trainings, we cover almost any topic you can think of, and we go way more in depth than we do in our YouTube tutorials. We have a private group where Matthew Reagan, myself, and our other industry veteran and pioneer teachers answer your questions every single day. If that sounds cool, click the link in the description to learn more. And if you enjoyed this video, hit that like button and don't forget to subscribe for more free TouchDesigner and immersive content.